slides?
Yes.
Okay. All right. So welcome everyone to Thesis Thesis Defense. We'll do this in the usual way, since the room is already populated. Instead of having a committee session before the exam, we'll just proceed straight to the talk. I hope that's okay with me. So Kara will present. Questions are welcome from the floor, from the committee at any time. Roughly speaking, aim for about 45 minutes to an hour. If you get interrupted, obviously it'll take longer, and we'll take questions all along if needed. If you have really involved questions, you might want to hold them till the end, because there will be a Q&A session at the end, both for the general audience, and then there will be a committee-only session when the audience will be asked to leave, and the committee will be able to grill KR without the rest of you here. So this is a coverage of a series of topics that Carol worked on over the course of her thesis. And so, time constraints mean she's not going to be able to deal with everything she talked about, so she's picked a subset. So yeah, I'll leave it to you.
Great, thank you. Welcome to my thesis defense on leveraging process transfer and sequential decision problems. This is the table of contents of all the stuff I'll be covering today. All the things in teal at the top were in my thesis proposal, so I'll cover them a little bit briefly. There's one final paper at the end, or one final paper at the end, fix the policy optimization that in my practices went over the time limit, so we will cover it very briefly, most likely, unless we have very few questions, which seems unlikely. I'll begin with our usual slide to introduce all the notation. We're working with sequential decision processes here, aka markup decision processes, where we have some agent, which we call, I can really see what they have signs up in it. What we call a policy, we characterize as a probability distribution pi, which takes in observations we usually call states or S from the environment, produces actions, and then those actions cause the environment to evolve. Few things that are distinct to the work here that are not in most other use of this notation. One is that I will also have multiple tasks, so I have these task variables X or Y, because we have so many tasks. Writing tau prime becomes untenable, so write X and Y. And also because we already use the subscript on policies or data batches for the iteration of the optimization, we'll also use the superscript for the task index. Makes sense? So the first thing I want to start with is a brief motivation of why should we care about transfer learning in robotics. And the motivation I'm going to explore is the cost of learning the last task. In particular, cost of that data for learning the last task. So if you think of a robot, you want to do potentially more than one thing. Some of those things you might have foreseen early, and you have a simulator, and you can easily collect data from about that task. And so the cost of that data is relatively cheap. But then you deploy that robot in the real world, where you have some more difficult tasks. And in that situation, you have a new task, technically. Maybe details are different, or you have a new door, you're in a new environment, whatever. The new task, you need data to learn how to do optimally in that task. And that's going to be much more expensive because you don't have, it's not a simulation, or you just don't have like a lab to do that development. And so there's a good reason to minimize the cost of that data. There's not a direct, easy to agree upon way of measuring that cost. So as a proxy, we try to decrease the amount of data required. And so from this comes two very frequently optimized objectives in the multi-task meta-RL kind of community. One is trying to minimize the total amount of data, which we generally consider to be a multi-task objective. One is trying to minimize sort of the last one, and that's what meta-RL has historically focused on. Although meta-RL also has some other objectives beyond just focusing on the data requirements of the last task. Great. So most of the research in this work uses the MetaWorld benchmark, which is a set of simulated 50 different tasks in a similar environment. They're essentially everything we could think to do with a simulated Sawyer robot that can't turn a stripper and also doesn't involve any like deformable objects. It's all rigid body objects. Each one of these tasks has randomized initial goal states and also randomized random initial states and also randomized goal states. Right. So one task is not a simple deterministic configuration. MetaWorld also comes with a set of task sets that have different properties, which is a set of pre-selected tasks. In this work, I'm almost exclusively going to focus on MD10 and MD50. They're just two different sets of selected tasks. 10 is a certain set, 50 is another set. And with these, the MT indicates the multitask, which for better world really just means the goals are visible. Whereas the meta RL tasks are like required to infer the goal as part of the partially observable setup. So when I began this work, multitask and meta RL were sort of the primary focus of the field. Meta RL began as a meta RL benchmark, but both these methods were really focused on trying to train one model, and they didn't really see much success in generalizing across tasks until very recently, and that mostly came out of multitask RL doing very large training runs on very large models. So I wanted to explore a different direction, which is instead of focusing on training one large model, what if we just try however we can reuse data across tasks, and we can use smaller neural networks instead. And then maybe use reinforcement learning, maybe to some degree we'll use imitation learning. So this just reuse data task, this just reuse data setting is usually called transfer learning throughout the rest of the community. In general, we transfer from some base task X to some target task Y. So that's the reason I chose those variables. So we'll take some data from the base task, or possibly the policy from the base task. We'll somehow use it to produce pi of the target task. Yeah. And there's subfields of transfer learning that have been focused more specifically, like sim to real or from internet to question answering. And I won't be focusing on those specific. You can imagine seeing those fields like sort of special cases of what I talk about here, but there's a lot of unique advantages of focusing that are not talked about this talk. All right, so now I'm going to go over the contributions that were included in the thesis to make that clear. First, we have a simple example of why you should care about transfer. We'll walk through the basics. And this was part of based off some work that was presented at Tuner workshops in 2020. We'll talk about the transfer cost matrix, which is a way of characterizing the difficulties of transfer between different tasks and when transfer is efficient or not efficient. That was presented at IROS in 2022. We'll talk about the transfer cost rule, a rule that allows predicting when transfer costs are going to be low or high. That is new work to this thesis that hasn't been released public before. And then we'll talk about two transfer algorithms that are short outcomes of that work. One is plan condition behavioral cloning, which will be presented at ICRA in 2024, so in a few months, and also fix the policy optimization to some degree. If you want the full details there in the thesis, of course. All right, so first I want to talk about a transfer example to motivate, get us familiar with the terminology and the location, and also motivate why we should care about transfer. So in this setting, we're going to treat different goal locations as different tasks. So here you can see a video alternating between 3 different tasks, and the tasks are just different corners where the robot has to drive to, or simulated robot has to drive to. And there's one policy, pi x, for each corner, right? So there's a pi sub top left, a pi sub top, or lower bottom, right? And the setting we're going to explore here is if you have a base task that was trained on a wide range of the state space. So it was started at a randomly initialized state and trained to move to the goal location from any possible state for maybe 100 demonstrations. We take one demonstration of the target task we'd like to do, that new goal location, and we want to produce the target task policy. So the reason that this is doable is because we place very simple geometric relationships between tasks. It's like easy to understand how to use an architecture to transfer between them. But again, this is where this becomes helpful. And so our setup is going to be just going to train a base, I keep expecting this to work. I'm going to train a base policy pi x, and then we're going to reuse the parameters in it to make a new policy pi y, where there are going to be some new trainable parameters that we'll find in the So we're going to explore 3 different ways. One of them will be to just add a new layer in front, and this is going to translate observations from the sort of space sy into the space of sx, right? We call that observation alignment because it aligns the observation spaces in some sense. We can instead try to do action alignment, where we try to translate the parameters of the action distribution from the x task space to the y task space. This basically does not work. So instead, what works much better is you try to replace the last layer with a new trainable layer that learns from that predicts the parameters of the action distribution from the final inputs. Do you have a question?
Why doesn't it work?
Why doesn't it work? If we think about it, there's just no geometric relationship for taking, if you think, okay, well, I have a point, I want to like have a policy that's an attractor to that point. If the point that I wanted to be moved, the attractor to moves, there's no affine transformation I can move, apply it to like the attraction field to move it. It's just like. Yeah, so just. If you think about it, it's kind of obvious that it shouldn't work if you like start looking at like, okay, well, I have to translate this vector and this vector, but it can't. So, why this works is a little bit more subtle, but somehow Z1 is useful affine, useful features that are somehow related to an affine way distribution.
Do you think you can extend by adding some non-linear items, like is that potential?
Yeah. So certainly you could. Well, I mean, it's not clear because we're freezing this. The information at this layer is actually quite small. So I would actually suspect that it would be almost impossible to learn any additional thing here, just velocity computational integration at this point. And really the fact that this architecture works so well motivates us in the future to just do retraining of the environment. Although this does have an advantage of it, you can't forget how to do anything in the early layers because those are frozen. Right? So it's a trade-off between forgetfulness. At least for now, there's a trade-off between like potential forgetfulness or being able to actually do the return. So here we can see a plot of all the three of those. The final one I described is the top line here. You can see after about 1,000 time steps of demonstration, it levels off at around 95% success rate. Adding one layer at the end doesn't work at all. Doing this observation transformation mostly works. It's a little bit slower, not as good. It's difficult to explain exactly why, but you kind of think about how the relative differences of these different optimizations are. Maybe it's different. We also tried. This is kind of interesting because of like how it ties into layer work. We tried combining the different sub-policies. So this idea of skill reuse that often shows up in robotics. Maybe we can reuse the base policies as skills and somehow switch between with skills that haven't with base policies that haven't been like tuned, haven't been trained to be used together. This barely works at all. It's extremely difficult. We have to use this. You can't like softly mix the outputs together. You have to hard some with it to work. Yeah, you have to like choose one of the base policies. And you have to like choose it for multiple time steps in a row. So we have like a specialized loss to fix this. And also, even after all of this, you still need like 50 episodes to make this setup work. So going forward, we focus more on single task transfer as opposed to multi-source transfer. Although I think that multi-source transfer has potential, it's just that it's a more complicated setup. Great. So hopefully
sorry, quick question. So that either that first layer or that last layer, one demonstration is enough to train it. Is that your claim? Yeah. Okay.
Yeah. Which is somewhat unsurprising. You're just trying to extract a linear layer from a few hundred data points. Shouldn't go. Configuring the blocks and the learning setup is slightly difficult because SGD is not particularly good at optimizing low dimensional layers. If it's like a low dimensional input, so we actually need to use like cross-config method on the imitation of the blocks to get the observational line to convert. Great. All right. So now I'm going to move on to discuss the transfer cost matrix. This project is based off work from at IROS in 2022. So in this case, we're trying to understand sort of the simplest setup of transfer on MetaWorld. So we can understand sort of the basics of like where can we do transfer across different tasks, when might it be useful, when is it not useful. Hopefully learn some useful lessons we can take from the project. So in this setting, we're gonna mostly focus on empty 10s. We have 10 tasks. You can see here a graph of 10 of the tasks. And I've added arrows or directed edges to the graph. And these edges represent transfer from one task to another. So we can have some policy by X, where X is a pick in place, and that would be the policy at this edge, at this X. And then we could transfer it to say push, what right here, drawer open. We transfer it to a drawer open, and that would be following this edge. not to reach with other tasks. To make this work, we need some operator to move us along the edge, some sort of RF algorithm. If you directly apply PPO or you directly apply even solve vector critic or any RF algorithm, it doesn't ever succeed. It just causes the policy to forget what it's doing. Because of this catastrophic forgetting problem. So what we found worked was just adding the same thing we call value function warmup, where you just pre-train the value function with Monte Carlo returns for about 1% of the data you normally use. And that's sufficient to give you a relatively accurate value function, and then RL training just continues as if it was like in the middle of the training. How to do this with Q learning is, as far as I can tell, still an open question, because for details of Q learning, starting with the Monte Carlo return estimated Q function doesn't necessarily work. Also, if we want to characterize transfer costs, we need to decide at what point we're done with a transfer. And so that requires us to not try to optimize to the optimal policy, but to optimize to some policy that's good enough. So I call these sufficient policies. So usually I will use just 90% success rate because it works pretty well for this picture. If we have a sufficiency criteria selected, then we can assign an edge cost to every one of those edges. We say, okay, we want to transfer from pick and place a drawer open, it'll take us this many time steps. And so we'll call that CX block. And so if you take all these elements and put them in a matrix, you have the edge weights of the transfer of the task graph, right? And that looks like this. So this figure contains data of two types. It needs relative data in the color, where this purple is the time it takes for promise. So you see the colors in the it goes up to 3 times. Anything in white or gray never finishes transfer within our time limit and doesn't work. Anything that is in the purple or darker kind of bluish spectrum here is less than the from scratch training time. And then I've also added the absolute number of training steps in millions at numbers. So it helps to see that visually. Here's the diagram explaining the different aspects. A million time steps learned from scratch is in purple. And then I've arranged this matrix so that the row corresponds to which task you're training from, and the column corresponds to which task you're training to. And there's an extra row here that represents the training from scratch, randomly equalized policy. So looking at this matrix, the thing that stood out to me the most, and which was most surprising relative to prior research, is that it is highly asymmetrical. And so if you look, for example, trying to learn workloads, which are an easy task from pick and place, it takes this 300,000 time steps, which is half as many as it took if you try to train from scratch. But if you start with workloads, and you try to learn pick and place, it takes over 12 million time steps, it never succeeds. Even though pick place does succeed on its own. And even if you renormalize, but based off of the cost of an individual task, you sort of assume, okay, well, it's not symmetrical because you can renormalize. The colors are renormalized, and they're also not symmetrical. And to show that more clearly, the rows and columns of this matrix are paired, right? The reason the diagonal is 0 is these are all places where we want to retrain by x to be by x again, which happens instantly. So the rows and columns are paired together, but the order matrix, if I can commute them into a new order, looks like this. You can see very clearly this is not symmetrical. Arguably, this is a almost lower triangular matrix. It's a large value. That's correct.
What's with the off diagonal zeros?
The off diagonal zeros are when a policy just immediately succeeds.
I think that's surprising.
It's a little bit surprising to me. It mostly indicates that the meta world is a little bit easier than some people expect.
What's the observation space here? Like, is it...
Yeah, the observation space here is the low-dimensional observation space. I can enumerate exactly each of the 43 dimensions are, but I don't think
it's
it's
an escape, not images.
yeah, notably, in that world you can't turn the gripper either, so it's like the object in the environment can turn, but the gripper is. So that's the observation. So yeah, the surprising outcome of this research was okay. The transfer cost matrix is asymmetrical for this transfer, at least for this transfer operator. Even under renormaling, which is not what people expected before, And this also has implications for any method that's trying to make use of transfer of sort of task distances. So even if you take some data about your task and you embed it into some latent space, well, then if you try to make use of distances on your latent space, those distances on your latent space will still be symmetrical unless you somehow encoded when you were looking at the task. This is a base task where this is a target task.
Okay, to follow up on the previous question, so is it exactly 0 or is it just beyond what you represent? For example, let's say you learn how to press the button, right? Button press top down. Now you can open a window with absolutely 0 training,
Yes.
or with
It actually works 0 shot,
very little.
and that I very much attribute to just how Meta World is. Like the most surprising cell from here actually that button press top down simultaneously knows how to open a window and close a window, 0 shot. Which if you watch the videos looks like kind of a miracle. It just like smashes the window, and on one task it happens to open, the other task it happens to close.
I guess the button top down is like a vertical motion, like if you hit the grip button, it's gonna slide a certain direction.
Yeah, it's like you see it kind of like it's something about like locations of the like the way that the window location is encoded in the low dimensional space just make button press top down just instantly work for both of those. Yeah, this research, you know, is the product of what we can do at the time. I do think that we will need to move on to harder things in Meta World soon, especially once I get to chapter 4 and stuff. So these are the takeaways. The other thing I didn't mention is that most of those cells were greater than 1, or relatively greater than 1. They're either white or they're like a light yellow. There's a whole half of it, excluding this one below diagonal cell. Or these two below diagonal cells are better than scratch, but the lower half is all worse. And then there's this region in the top that's also worse. I didn't actually run an optimization procedure to order it. I just manually ordered it. So there may be a way to remove this to make it closer to diagonal. But either way, the majority of the transfer edges are much worse than training from scratch. So most of them are at least 3 times worse. So if we want to use this information directly to try to learn all the tasks, we can imagine extracting a tree from the transfer from the transfer graph, where we root the tree at a from scratch node. And in this case, a tree is just the direct minimum spanning tree of the transfer graph with the CXY edge. But so in this case, an optimal tree is one of the optimal trees is this one. There's ambiguity because of the 0 cells. And the selected cells that actually use are these things. If you try to do this, it's actually very it's a challenging optimization problem in that most of the trees result in performance that's worse than from scratch. So let me explain this figure. If you choose a sufficiency criteria, say 90%, once you've chosen that sufficiency criteria, you can then try a variety of different trees along the sufficiency criteria. So in some sense, interpolating here, the reason that the success rate is on the x-axis is you have to choose it before you run the tree. If you only run the from scratch, I guess it would be a sum. Your performance of this or costs to acquire the entire tree as long as it's dashed green. And if you choose a random tree, you get the red, which is worse by I think 2-ish. But if you choose carefully the optimal curriculum, this is this blue line, you can do better at some sufficiency criteria than the from scratch tree. So there's this, okay, it's mostly invisible now, but there's this gray region here between the dashed green and blue lines. And that's the only region where it's preferable to transfer instead of doing from scratch. Also notable is that to do that, you need to know the tree. But you got the tree from running all the possible transfers. So this sort of issue with trying to use this for practical purposes. So I came up with an inference algorithm that tries to predict the tree online. Since the idea is we're going to have a belief distribution for each edge. It's the gamma distribution predicting how much time it remains for training that edge, the sufficiency. What we do is we sample the remaining costs, and then we produce a tree from that remaining that sampled costs. We run one step, and then we update our belief distributions. It's like a sort of a sibling of Thompson sampling. except that instead of sampling based off of what's going to give us the most reward, it's what gets us closer to sufficiency, which is sort of a thing you're constantly getting closer and closer to. So it doesn't have the like asymptotic difficulties that multi-arm madness typically have. So unfortunately, this is also very computationally expensive to do experimentally because you're trying to run a long transfer run and trying to run many of them. In the meantime, the actual performance of your RL algorithm is not particularly good. So what I did to do these experiments is I took the original set of runs, which have some total cost here for this green line, and I ran a bunch of simulated runs where I just replayed the same runs a bunch of times to simulate how inference transfer probably works. We get this red distribution here, where sometimes we infer a better tree, sometimes we infer a worse tree. But most of the time we infer a somewhat better tree, about 10 million or 7 million time steps. And then I actually went and actually ran the algorithm live on real runs or additional new runs, so to speak. And that gave us these green lines and dotted blue lines. The dotted blue lines are the time it takes to train from scratch stub, and the green line is the transfer. And what you can see is that the variance across runs is significantly higher than the effect size we're looking for here. So these results are not statistically significant, even though I spent a few months of computing this. But the average effect size roughly matches what we see in simulation. And really, this is pointing, in my opinion, to you need to make your RL algorithm more reliable if you want to get better data from its algorithms. Does that make sense? This plot is a little bit good. One thing to note is that I do time out from scratch runs because they often try to do all the from scratch and just one of them times out. So there's a little hump here that's from scratch runs timing out. So to some degree, you can think of what inference transfer is doing. It's sort of being similar to like a a population-based training method almost, in that we're trying different ways of acquiring the same task. So if one of the runs fails, it succeeds. You could argue that most of the results here are because of that kind of population effect being useful without having much transfer. Recap: transfer matrix describes the relationship between tasks. It's really asymmetrical. Value function plus PPO plus value function warm-up does work. Notably, without value function warm-up doesn't work, but it's also quite noisy as base PPO is. All right, so now I want to talk about a mathematical rule I found for predicting. Yes, just me.
I had a question on the previous slide. Actually.
Okay.
So I really like the idea of learning structure between tasks and trying to quantify like how hard it is to transfer policy from one task to another. But I noticed that a lot of your investigation is into like model-free methods. I'm wondering what kind of results you would expect from model-based methods.
Hopefully better ones, but I don't have a strong statement about that. Yeah, I think that probably model-based methods you should be able to transfer better. In that, I would expect you can somehow make a model transfer more easily than the policy. But there's a reason we'd expect the model to transfer, which is that, okay, we're just sort of extending the natural set of things that the model could reason about. Whereas with transferring a model-free policy, we're saying, okay, you were doing one thing, now learn to do something else that kind of contradicts your original behavior. With like a higher dimensional observation space, maybe both of these are more like, both of these might be like more adding as opposed to.
Would you then always recommend people to go for model-based method if they're trying to do multitask learning, or is it kind of dependent?
We're in an odd space where like model-based methods I think are about to get really much more interesting because we have like actual good video synthesis. So you could do model-based methods from pixels, which you couldn't do before. But I'm not an expert on the topic.
I'm curious to know if you could get like working through the image observation space. If you like using a pre-trained model, you might be able to like have object relationships, in the sense that like maybe some objects are easier to manipulate given we can manipulate the hard objects and this. If you have any thoughts on how you could do the image based
Yeah, I mean, there's definitely something there of like, okay, I know these objects are similar shapes, similar weights, they're both rigid, therefore I could expect that these same policies pick them up. But not really what I was looking at in this case. Now I want to discuss the transfer cost rule. Mostly this, to some degree, is useful because it can tell us, okay, when can we transfer, as opposed to having to empirically go out and collect a bunch of transfer runs to see which transfers work, or having to sort of infer online but not really know why something is working. Maybe this can tell us something about why a transfer is working. So the key artifact that I found really essential to predicting transfer is what I call the behavior distribution. So other people may have called this different things in the past. This is the total distribution of our state functions, the state action distribution that's caused by running the policy by X, potentially on a different task. So just task one. So BXY here is running by X on task Y. It's a distribution across states and actions. Make sense? If you know a more conventionally used term for this distribution, please let me
This is losing information about the temporal ordering.
know. Yes.
Because you're just looking at.
You're completely discarding temporal ordering of information. You're just looking at individual time steps. Notably also though, functions of the behavior distribution are likely to be non-Markovian relative to the original distribution. Because you're characterizing a set of states, not an individual state. So the transfer cross-flow I found that works most effectively is to compute the tail divergence between the cross-task distribution of pi x on task y and the distribution of a submission policy pi y on task y. Where pi y here is the closest or implicitly minimalizing the tail divergence of pi x. And then you use some coefficient that describes sort of how difficult the task is, which we can also interpret as some way of converting the units, which the tail divergence measures the relative entropy between two distributions in NATS, and it converts them into time steps. Sort of.
Sorry, to compute BYY, you need to train, right?
If you compute BYY, you need to train pi y, or you need to like collect demonstrations of the task.
Okay.
So
Because if you are trained, then
you need
you
yeah.
don't care about transferring from X to Y anymore. That's what I mean.
There's this does not solve all problems for you, but if you want to know, okay, if I have two demonstrations of two different tasks, or maybe I have two ways of sort of approximating distributions, I have, say, videos of the state spaces or state space, videos that I can chop up to make a bunch of images into the state space, and maybe I can characterize this distribution approximately and that distribution approximately. Tell me when
I mean, without knowing the action, so just from the videos, yeah.
potentially.
So that first, the coefficient only depends on y and not.
Yes, that would work. Is it W only? And so you see how you actually run this. Is it I think the general fit is you actually kind of already do it. And these terms actually fit just a Gaussian, a multivariate Gaussian to the collected data, flow dimensional. But yeah, how to get WY is also sort of unclear. This is sort of the efficiency of the algorithm on task one, which is not something that's easy to characterize. Like how efficient is PPO on big inputs? Well, this gives you some measure of okay, it converts, it gets like this many NATs per time step. But how do you know that TVO gets that many NATs per time step on the second place task? Well, you just have to run it basically. Still this tells you something about how tasks relate to each other. So I don't have behavior distributions of the original PPO runs or the neural networks, so I can't directly run their cross behavior distributions. What I can do instead is I can take the scripted policies that Metabol has and use them to collect cross domain distributions. So these are a little bit of a awkward proxy for what happened in the original transfer cross matrix. So this is the data of the original transfer cross matrix, and how well this rule works in predicting. So the x-axis here is the behavioral scale divergence. To make the scale divergence well defined, I have to add a small regularization term to the diagonal of the covariance. So basically, I'm assuming there's like some minimal variance each dimension. The reason for this is that some tasks just have like fixed objects at different locations. So behavior distribution is like.
So what's the motivation behind using the behavior scale divergence instead of, for example, using a behavior cloning objective?
So yeah, we experimented with doing a cross behavioral cloning loss. So you train a policy for X, train a policy for Y, compare the behavioral cloning loss on X of policy Y, and so on and so forth. That's what we originally did for inference transfer. And it mostly kind of works in that you get some type of relatively like true prediction for some of the meters. but it really doesn't reproduce the asymmetry, is the problem. Do you really,
What do you mean?
like the transfer cross matrix has like the strong asymmetry property, right? Where some transfers in one direction, the edge is much lower cost in the other direction. And this cross VC loss isn't really able to reproduce that asymmetry. Maybe think about like this. Maybe you think about like why it's like not too surprising in that. Like the action, just like the action. Yeah, maybe it's maybe a little difficult to like directly think about like why the cross behavioral cloning loss is not as effective, but it's mostly more symmetrical.
Yeah, I think it's probably because of like the criticality of states, right? So for one task, like making a delta mistake is fine.
So that's definitely one element. Yeah, is that like some actions are much more important because they result in a different state distribution.
Like the peakiness of your Q value is like the advantage.
So notably, like tasks or policies that like begin by picking up objects are going to transfer very well to say the push task. Even though for most states they may have like very similar actions. On some critical states where they pick up objects, much slower. So we have a pretty good R-squared value here on the original data set just by using this proxy. That it partly depends on flipping away really high values in scale divergence, which we look at that either way. It's sort of a subjective judgment on my part. We can see a fit here of the data. The from scratch points I think were relatively clear. Why more importantly, we're able to sort of separate out the all the points that time out are at the very high end of the scale. So we've taken half the transfer cost matrix, where those are all the very expensive edges, and we've clustered almost all of them right here. So that's useful to some degree and indicates that we're looking at some part of the structure here with this very simple. Probably better numbers with actual cross behavior distributions where I actually ran the policy for one task and other just tasks. And so what I did is I ran a bunch of runs of an algorithm I call FixBO. I saved all the intermediate behavior distributions during training. And so that lets me compute a bunch more points in this fit. And here we can either use one W value per task, which gives us fairly strong, I think, for this type of task, for this type of setting, fairly strong R-squared values of around 40%. That's making it charitable, 35%. But if you share one W value across the entire benchmark, it also still works to some degree. We see similar predictive power across the different steps of a from scratch run as we do across transfer routines.
The previous slide. Visually, it seems to me that the error is pretty large, like on the y-axis around, cost rule, if I look at like the spread seems quite large.
Yeah.
Why is the R-squared value not that high?
So this is a log plot, so that's partly what's contributing. Is it
But I almost think it's even worse then, right? Because
yeah, so there's a couple things here that are like
for example, like if I just take, I don't know, maybe it is tricky because there's also points below.
so the reason that the fit is predictive at all is really the extremely high density here. But these are all the points that timed out, and they're all being clustered. Whereas the remaining points are sort of in this somewhat unorganized region with lower rate of that.
I'm just a little surprised, like I would have thought it would look worse, just somehow the spread, because it's a log plot, I feel like if I take any horizontal vertical slice, it feels like the spread is quite,
Yeah.
2 orders of magnitude.
So the notable thing about a log plot is that the spread on the left is discounted relative to the spread on the right.
I see.
Yeah.
I see. I see.
Which looking at this data without, part of the difficulty here is that I'm using these certain policies and it would really high terms.
I see what you're saying. So
which-
basically, it doesn't even really account for what's happening.
Yeah, the problem is the scripted policies are fairly deterministic. So they just tend to follow the same state path, which doesn't give you a very wide
Range.
behavior distribution. Where I have a similar plot for an actual run of picket or for a set of picket place runs. And here, this is a linear plot. You can see the linear structure. Obviously, there's still a lot of noise. There's some like tails here of like high tail divergence. It's actually not that far from sufficiency, but the general sort of linear trend is not clear. And to make the density clearer, I've done a sweep across the tail divergence. And you can see the distribution of data points. So here I also have I've went partway to re-implementing inference transfer. One of the important steps is having a probability distribution describing how much time remains. So this red dashed line is the PDF of a gamma distribution predicting how much time remains at any that hopefully there's a little bit of a caveat to this data, which is that these points are not fully empty, but because they came from the same like different points of the same there are 100 runs on the supply. So I think they're IA within plus 90% essentially. So I want to talk a little bit about theory and like why we expect this to work. You could imagine a transfer algorithm that when it sees the taking place policy just refuses to do anything, and therefore, like when you try to predict when you try to predict how well this rule is going to work in different tasks, it's always going to perform really badly with an X taking place, right? So we're not going to be able to prove anything about arbitrary transfer algorithms because that's a very big space. So what I'm going to do is I'm going to propose a very simplified model of how an RL algorithm works that sort of is based in information theory. And then I'm going to show what conditions on that model result in the transfer cost rule being true. Also, a little bit of background. One important thing to remember, so a little bit of small amount of background information theory for the next two slides, which is important for understanding what we discuss. One is that information can be measured in amounts, which we're probably used to computer science. There's bits. The tail divergence actually measures in NAT, which is like this unit of sort of the natural log equivalent, or the one constant equivalent of bits. And also the amount of information produced by an event becomes less as you expected that event stronger and stronger. So if you expect an event with almost certain probability, you get almost information from that, observing that event. This slide is to hopefully explain why the tail divergence goes from right to left, which is that's the direction the tail divergence naturally goes, similarly to conditional distributions. So this example is talking about if you imagine the sort of the classical task of I have a jar of marbles, I pick out a marble, I look at the color, and I want to eventually estimate from a sampling with replacement from that jar what the ratio of red to blue marbles is in that jar. Right? So you might have simply distribution pi after pi sampling batches. If I update that distribution from pi I to pi x 1, then the information I want to observe to have done that with a optimal inference or the Bayesian optimal inference algorithm is the tail divergence between those two probability distributions is the information relative to between. And it all goes from right to left, which is why pi xy is on the right of the figure possible. And that's important because that's where the asymmetry came from. Right? So. Great. So fundamentally, the main reason the transfer cost rule seems to work is the assumption that if we model our algorithm as just repeatedly doing improvement, so we're taking the data batch on pi I, we get pi I plus 1, is that somehow DI, the data we use to do that, contain a constant amount of information at each training step, which is not what I intuited going into this as an outcome. And my model of the transfer algorithm is just that the expected I, so the number of training iterations we expect to get a sufficient policy pi y out, is just going to be this sum of information should equal the K distribution difference. So that makes sense of why this is maybe a reasonable model. Notably, this is pretty far from how PDO actually is. PDO does not appear to be anywhere close to the information optimal. And also, if there were other sources of information, somehow there's information in pi I that allows it to suddenly increase the behavior distribution significantly partly through training, then that could also sort of be a hidden source of information from inside the policy. And so also we need to assume the R algorithm is forgetful for this.
Can you give us a little intuition? Why is it that the expected information gain is independent of the base counts? Thanks.
Right, so this is what I'm saying is, if the transfer cost rule is true, or if these conditions are true, then the transfer cost rule would predict the expected cost. So we're just saying, okay, if we assume these rules, then we get the transfer cost rule. So why would the information gain be constant? Is a good question, because we have sort of conflicting intuition. On the one hand, if you have no prior information, a data batch is very close to pi y, is definitely more informative than a data batch that's far away from pi y. On the other hand, if you have pi I, then data batch di may not be that informative in that you already have a prior about what's going to be in di. So these are sort of conflicting intuitions about whether or not the information content should grow or shrink during training. In terms of, or we don't think about it as in terms of what time for training you need, but in terms of base task. So these predicting what's the word I'm looking for? Conflicting intuitions. Maybe surprising, there's sort of conflicting intuitions, and the prediction here that I'm making is that, okay, if the information gain is constant, the transfer cost rule will work. I observe the transfer cost rule working, so maybe the information gain is constant. Another prediction we make from the transfer from the information being constant is the failed divergence of behavior distributions of adjacent training steps should be approximately constant during training. So we shouldn't see the behavior distribution like suddenly rapidly shrink at the start or at the end of training, or suddenly rapidly move. So we definitely imagine settings where it tapers off rapidly, or it increases at the end as we get close. But what we observe in practice is it is fairly constant, although noisy. So here the blue line is scale divergence between adjacent policies during from scratch runs, and the dashed green line is scale divergence between adjacent policies during transfer runs. The right side here, this is on the x-axis, we have the remaining training time steps to the end of the transfer run. So these are all aligned based on the end of the run, and there's 1,500 runs on the squad. So at the end here, at the very edge, we actually like this data point, only a few runs are actually going to need for this data that are going to be 5 million time steps away from sufficiency. So there's 1,500 runs at this edge of the block. Once we're over here, there's only 5. So here's a little bit of a slight increase at the start here, which indicates that like for some of the slowest runs, they started with the biggest steps at the start of training. But besides that, it looks fairly constant. Although very right. There's also this idea that why else could DI not give you constant information? You could imagine an environment where some states tell you a lot about how to perform well in the environment. So in a pixel-based environment, you can imagine you're in a maze, you find a map in the maze, right? The data that contains that map is super useful. And you can imagine an environment where like halfway through training, on average, you find that map, right? In which case you'd expect this curve to like have a big discontinuity for once in the middle, where like all the policies are finding the map and rapidly changing. Or perhaps that would be like near the end of training here. But we don't observe that with these. So maybe that's just an artifact of meta world tasks being sort of piecewise linear-ish environment tasks with a constant reward function. So you kind of are constantly getting, or like a smooth reward function, sort of constantly giving you more information. So there's different reasons you would expect this to probably be true for our environment. I also briefly mentioned that like there could be, if there were information somehow hidden inside the policy, maybe the total cost would be lower, in that instead of having to think about the starting distribution, this is backwards. The map here is completely backwards. Sorry. That's just wrong. Yep, this should be the other side. Instead of having to think about the tail divergence of behavior distributions, you couldn't only think about the tail divergence of the action distributions on the sufficient distribution set. So this is sort of like the equivalent of how far is the trade policy on the actual states that you need to solve the task, as opposed to the current state distributions. Apologies for this being. Which potentially this could be much lower, at least intuitively. I don't have comparison numbers for this. But avoiding forgetfulness, as I described, it seems to be a major theme in a lot of more recent transfer learning work. So, kind of a recurring theme. I expect it'll keep showing up in other people's work on it. And this sort of gives us one perspective on why. So hopefully, you understand why I think that characterizing behavior distributions is a useful way of comparing different tasks. Even if we didn't get 100% predictive capability, or even 50% predictive capability with the transfer cost, where we see definitely some of the structure. And there's this prediction that information gain is constant throughout training, which maybe that says something about our benchmarks, maybe that says something about our algorithms. But it seems there's an intuition that it shouldn't be. Maybe that's worth thinking about. And also reducing forgetfulness will continue to be a theme, we expect.
So, like, I was wondering if you had like made for future work, do you think that the clear divergence between the behavior distributions and as a measure could be like include that in some way? Like, what's like the
Yeah, so you could imagine writing an algorithm that directly tries to optimize the behavior distribution, or sort of uses that as like a primary objective. Notably, the K divergence of the behavior distributions is not Markovian, right? You can't just like adjust the reward in a way that matches the reward distributions, because there will always be some maximal reward path for your distribution and for your environment, and that maximal reward path, or like attempting to follow that maximal reward path, won't necessarily follow the behavior distribution.
so maybe like something like the advantage weighted clear divergence.
It's so the K divergence is not Markovian. So if you want to write an algorithm that does like behavior distribution matching, the behavior distribution K divergence is not Markovian. So if you want to somehow write an algorithm that does behavior distribution matching, you're going to somehow need to do something a little bit more careful than just augmenting the loss of individual state action pairs. You can maybe do some type of like Lagrangian optimization where you like select encourage the policy to like visit parts of the behavior distribution that mismatch, perhaps.
Because I can think of like, let's say you have two behavior distributions and because you might have a different set of critical states and one a different set of critical states than another.
Right.
So if you like weight it by the states by the advantage, and I guess like you would be able to align.
Right, yeah, so you could definitely imagine how you could write something, an algorithm somewhere between like an imitation learning and reinforcement learning algorithm. We have like demonstrations or somehow you're trying to match behavior distribution, and you would somehow analyze like what are the specific actions that are causing behavior distributions to mismatch. Also, I think that there's potential to do like thrust regions in behavior space, which I think is an interesting direction for future work. Whereas current thrust region algorithms enforce thrust region in action space, which can be not sufficiently weighted, but there's a high degree of different criticality in different states.
So you're saying like mismatch between the thrust regions of how
I mean, it can be arbitrarily high in the case of pedal, where you can have like a pick and place task. You've grabbed a puck, you can drop the puck in one action, and you're down 400 time steps out of 500. So, and so there's this open question of why information gain is constant throughout training, which maybe that's not true in many other cases, but it seems to be true here. And what does that say? These are open questions. Thank you for there's this question of like, why is applying information theory a good idea at all? It sure looks like PVO is actually pretty far from the information theory boundary. And then also I have a method that sort of avoids collecting cross-task demonstrations, which is sort of the weirdest part of this method. Where you can try to take state distribution or the behavior distribution from one task and project it onto another task, but it's not a principal reason to expect it to work, but sometimes it does. And that seems like a direction that might be possible to explore in the future. All right, so done talking about the transfer cost rule. Now I want to talk about one, potentially two, so probably one.
That's the other one.
One transfer algorithm. where we are going to mix together skills using language. This is going to be presented at IFRA in April, wait, not March, I think.
It doesn't matter.
Okay, anyway, moving on. This is a continuation of intern project in Google Brain, back in Google Brain and Google Brain. The idea is that we can somehow ask a large language model to produce a plan for us that says under what conditions we can reuse different skills. And then hopefully we can use this to match up skills between different tasks, and somehow we reuse skills. In the process of doing this work, I created this benchmark called Language World, basically augments Meta World with task descriptions and also a query answering function, which is sort of the sort of an equivalent of like a like visual question answering module, except scripted and therefore much more efficient. This is available for open source, everyone use, please use it. So what we're going to do in this project is we're going to create a language model to output some code that looks like this, and we're going to have a second neural network interpret this code. So our conditions are some sort of semi-structured natural language statement that our query module can answer, and our skills are actually secretly natural language string. We're just going to take this method call and we're just going to embed it into a continual space. If we look at what the language model input and output looks like more precisely, exported just like this, we'll have 3 tasks where we'll give the language model an example of how you can split that task up into mapping between conditions and skills. We'll query with the description of one last task, and then we'll get a mapping. So the full system as a block diagram, we take in that prompt, so what I just showed you on the previous slide happens right here, and then the language model produces a plan for us that maps conditions and skills. Then we have a data set of demonstrations that we're going to use to fine-tune our interpretation of those plans. And so how we're going to do that is we're going to take the states, we're going to interpret, we're going to evaluate the conditions on the states to select which skills to use, and then we're going to use a softmax to mix the latent representation from the skills. So this is just a pre-trained language encoder. We're not going to fine-tune it, so we just, when we get an output from a language model, we just say, okay, either of these skills becomes this vector of what the language encoder thought this thing meant. So we can mix those together. So maybe we have a skill output that says something like put your gripper over the door handle and half put your gripper like down. And then we have this action encoder where all of our actual trainable neural network parameters are. It takes in this skill representation and also can observe the world and then outputs information. Because this actually occurs at the end, we can fine-tune it using just an MSE loss, behavioral cloning loss. We call this plan condition behavioral cloning because we're just conditioning behavioral cloning on the. Thank you, Ryan, for coming up with this name. Critical to how this works is we want to still be able to do some type of transfer between tasks. And I found that this method works very well. In fact, this is almost the strongest part of the paper, where we do something I call cross-task co-learning or sometimes one-to-one data mixing. The idea is that instead of taking all of our data and just sometimes running different batches from different tasks, what we're going to do is we're going to take data points, just data action pairs from each of our tasks, and we're going to label them with what task they're from. And then in every single mini batch, we're going to feed in a balanced number of data points. So half of our data points are going to come from our base tasks that we're not trying to optimize for. And for each of those base tasks, we have an equal number of data points. And then half of the data points will come from the target task. So that visually, hopefully, makes sense. So the first result I want to show you are two-shot results. This is a conditional probability distribution style diagram where the success rate is on the y-axis. On the x-axis here is the number of tasks that have at least that success rate. So you can see sort of at the right here are 10 tasks that are easy and have almost 100% success rate. And then at the edge here we have some harder tasks. On this plot, you can see the results of just running scripted skills that are linked with language world. You can try training on only 10 base tasks and then try to transfer zero shot with a plan, but without any demonstrations to another task. In that case, we start with 10 tasks where we have 100 demonstrations, and the zero shot generalization goes up to 20 tasks-ish. but something. Arguably, it's 100% generalization, it generalizes to 100% more tasks than you train them, but it's kind of arbitrary. If you instead have 10 demonstrations per task, including your target tasks, you do somewhat better. So many of the tasks, how now the fall off instead of being very sharp, much more gradual fall off. So those 10 demonstrations of each of the 49 tasks you can use as base tasks, those like 500 base task demonstrations, are allowing you to somehow slower fall off. And also get 10 demonstrations of the target. So some tasks still are not possible at all with demonstrations. The success rate is still 0, but a lot of the tasks have a higher success rate. So the plot that I'm most proud of is this one, where instead of having 10 demonstrations of each task, we're going to have one demonstration of the target task, but 100 demonstrations of each of the base tasks. So in this setting, I just use W10 as the base tasks. So 10 of the tasks, for 10 of the tasks, as long as it is on the current target task, you'll have 100 demonstrations of each of those tasks. And then we'll train one neural network with one target task demonstration and either 1,000 or 900 total base task demonstrations. And the performance we get actually does not ever touch 0 throughout my experiment. But data training, we actually generalize out all the way out to the edge of the number of tasks we have, although the success rate does drop very low. And here you can also see the difference between just hitting on the task description, which is the dashed green line, and using plan conditioning, which is the blue line. You notice it like it's about 10% higher. 10% higher, and also the tail is just longer.
Just to clarify, that's average success rate across all tasks on the y-axis.
No, the y-axis here, this is a conditional distribution. So nowhere here is the x-axis is not time, the x-axis is tasks. So this is saying 20 tasks have like 90% success rate.
But on all of them, like it's.
On 20 tasks.
But like, success rate would be averaged or tasks.
The success rate is computed on one task. So say the pick and place skill is right, the pick and place task is right here and has a 90% success rate. And then next to it might be the drawer close task, it's a 90% success rate. And so on and so forth. Right. There was a version of this plot you could hover over to see all the tasks at each success rate. This is across 4 seeds, and the shaded region is actually like the minimum and max. So there's no confidence interval here today. This is as large as the data range ever comes. Questions about these results? These are possibly the strongest imitation learning results ever presented on.
So just to clarify, that's like the index of the task.
Yes.
Okay. So it's not a number of tasks on the next, like it's like saying.
Yeah. Okay. Maybe this should be in there.
Well, if it's not coming in the system, or you get the number of tasks.
Right, but then like you can misread this part and think it's average across all of the, it makes it 50 tasks, you think 20.
Okay. Yeah, that's a fair criticism. I don't know.
But that's just fine.
There's only so many ways I could. The flow description says this is a cumulative distribution function style plot, and I think that gives it up pretty much. So there's this project. I think the numerical results are pretty good. I hope language world is also useful for the rest of the community. There's also several open questions that came out of this work. One is that the optimization regime I found where this worked is fairly computationally intensive. I used 500 training epochs and these small mini batches, and also the models that were relatively large, so like 256 neurons wide. So which of these aspects is most important? I'm not going to answer, although I think Shashank has already begun investigating, so hopefully that'll be answered eventually. Here we're kind of just using a differential interpretation of a switch statement, and we can definitely do something more sophisticated than just switch statements in the future, but that's what we limit ourselves to here. And also here I use this like 1-to-1 data mixture, and like maybe that's not actually the optimal ratio, especially with a very large number of base tasks. It's time for the last paper. Do you think I should just one slide?
Yeah.
Okay, one slide. All right, so this project, and the reason that this project is important in my perspective is that a lot of training when we're doing transfer, we have our target task loss, and we also have some base task loss that we're adding to try to avoid forgetfulness, or like this, the left half of the mini batch that I showed before. And in which case you might want to have some coefficients, you don't focus on them too much. But you also probably want to make sure you don't completely forget the facts. You want to like make sure the loss doesn't grow without bound. What we found is that if you instead of trying to enforce a hard loss here, we instead split this into a soft proximal loss that you enforce with Lagrangian methods or deep Lagrangian methods, and then you occasionally add additional gradient steps whenever you hit the hard boundary. You only need to hit the hard boundary like 5%, but only like 5% additional gradient steps. And also this works well as a trust region method, a trust region, single task trust region algorithm. Where you kind of get the guarantees of TRPO and trust region methods, but you have the computational properties of PPO, where you're not doing a optimization of the policy. So hopefully that's interesting. Okay. Going to skip the rest of this paper. Here are some other contributions in my work. I wrote this experiment runner called DoX that knows how to take a script of experiments and will rerun the ones that haven't run yet. Super useful if you don't have something like this. Write yourself a tool like this or scale mine. Okay. MetaRoll, I was the lead maintainer of MetaRoll for 2 years, which I think is a fairly reasonable recent contribution. Language I already discussed. I also helped create Garage, which is a meta and multi-task RL framework that's still somewhat used to this day. I'd like to thank all of my collaborators in the lab here, my co-authors, the people who contributed to MetaWorld and Garage over the years, people I worked with at Google Brain when I was interning there. Amazon graciously funded me for about 2 years during my PhD, which was very helpful. Also, some of my anonymous reviewers were very helpful. Some of them were. Yes, sir. Here's a summary of all the stuff I did during my PhD. It's also available on my website, or if you want to take that. So thank you for coming.
The QR code lead to.
The QR code leads to these slides. Yeah.
All right, we're open for questions. Maybe general questions from the audience first.
Go to slide 2. I added a jump to slide box.
I can get it started if you
Yeah,
want to
go ahead.
round people up. So we already discussed this idea that your KL between those distribution of state action pairs discounts temporal evolution. Could you use something else, like some string editing distance or something like that across runs?
There's a few meta-RL methods that instead try to use like a recurrent model to encode the task.
Similarity.
So, but usually those frustratingly, those methods, all the methods that I'm aware of that did that, tried to encode the task and then encoded it into a single link code, and then tried to do the distance between the linking code. So they, even though they went to fairly large lengths to do this like temporal reasoning, at the end they assumed the structure was symmetrical. So like this is what Perl and Catch were doing. We're casting that as well.
Yeah, my question is not like, is technology matter like zero distribution? So imagine like, let's say that there's a task that starts back here and you have to walk all the way to the front. And the other task is starts at the front and walks backwards. The actions are like basically the same for every state. Like
I'm not sure the actions are the same, but
No,
actions are probably the opposite.
not in this task, but like imagine that you just like flip the order, the MVP is reversed, right? Like somehow that,
Right.
I mean, forget about.
I mean, to some degree, I think that the Markov property says that you shouldn't care about sequentiality, except as it belongs to later state distributions.
It says like in both tasks, if the right action you take is always the same,
Right.
it doesn't matter what order the states appear, like.
Right. So the Markov property kind of argues that maybe the order the states are in doesn't matter. Right. If you're in a state, then it doesn't matter how you got there. And the actions sequence of actions that shouldn't matter, except that some action might allow you to visit a new part of the state distribution. So the limits of analyzing the behavior distribution are that you're throwing away the temporality, but to some degree, the Markov property is already having you throw away most of the temporal structure.
So I guess like temporality in theory isn't like the reason doing like the behavior, like behavior distribution is a reasonable way to figure out what are the set of states that actually you see on the, under different tasks, right? Like the demo in theory doesn't matter.
Right,
It depends on what you call state, like you could call state a sequence of states, and then you have to go to initiate a state.
right,
Because like just saying, oh, Markov property means temporality is
Right.
is like a very
so everyone doing RL fine tuning of language models is treating like the entire history of the conversation as a state, yeah. So you could imagine instead of just fitting a Gaussian distribution as I did here, instead of having a sort of generative model that somehow is doing some type of like contrastive learning that like knows the likelihood of like sort of doing like the deep equivalent of a permutation test, like knows the likelihood of like some parts of the states being exchanged between two different distributions.
I guess the challenge with that, especially in like pixel-based environments, is concatenating a sequence of images and reasoning over states that way. But maybe you could do this for state-based like tasks. Like,
Yeah, I mean, I would probably do like if I were doing this, I would probably do like deep sets and then do like a contrastive learning where like you're trying to separate, you have like a bunch of frames, they've been shuffled together from the two different tasks. You have a network that's trained to like separate them back out again into the two different sets. Sort of clip style. And then you can probably characterize the tail divergence as like the likelihood ratio with these output across the two different. So the tail divergence, I didn't get into it here, but it's formally the like weighted like in like the weighted likelihood ratio of every possible element of the distribution. So you can like do a finite sampling of that with some finite number of states and like integrate out. You can like approximate with the summation, be like approximate tail divergence. If you have some type of like if you have a function that can if you have a neural network that can categorize which tasks the image came from, you should be able to then approximate tail divergence of the data distribution. But that's a little more involved than fitting a Gaussian.
Compared like fixed PO, I guess, with like other transfer learning approaches that do like maintain a copy of the network.
Yeah, so I've only done very minimal fixed PO transfer experiments. And in particular, the experiments I want to do is use the offline or off policy trust region to like avoid forgetfulness while transferring across multiple tasks. I haven't actually done those experiments. So the most interesting experiments haven't been done, partly because there hasn't been a way to put that into a paper. So, and also just like sort of depends on prior work.
Let me ask one more. You know about adversarial reprogramming?
Adversarial reprogramming.
It's like an extension of adversarial attacks. So with adversarial attacks, you have a picture, you add a little bit of noise, and you can code the optimist back. So you can do that at the task level. You create so you learn a noise pattern, which will transform a network that was trained in a particular task to now perform a different task.
Right, I imagine it's like similar to like prompt attack.
Yeah, so it was originally for image classification. So let's say you have a classifier that is trained on ImageNet, then you design a noise pattern that you're going to put around MNIST images, and your classifier now, without any change in the weights of the model, just by adding that noise pattern, you are basically getting an MNIST classifier. Okay,
that's really interesting.
I was wondering whether that could apply also to your work instead of having to the first or last layer of this kind of thing. Maybe
because you can see observation alignment as a very crude way of doing that. Partly a lot of these adversarial attacks are possible because you're operating a very high dimensional signal space. And so adjusting a very large number of dimensions slightly lets you significantly influence the output of like the early linear layers. But I'm not doing those types of environments here, so it's somewhat different.
So you're saying because you are not using the pixel data, right? You are using this 34-dimensional something.
Yeah.
So yeah, maybe okay.
It's much harder to do an adversarial attack mode dimension.
Good answer.
So there's definitely something this is sort of a similar intuition for why observation alignment might be relevant beyond the very low dimensional setting, is you could do something like this, but I'm surprised that really works so well. To be honest.
Right, maybe what we do is we just switch to the committee section, there are no audience questions. Thank you.
Bye, KR.
Thank you all for coming.